All right, I'm gonna go ahead and get rolling. So thank you everybody. Welcome to the start of GRCon16's technical conference. I'm gonna run through a few logistics here before we start the program. So for anyone who was here yesterday, a few things have changed, all for the better, I think. Let me get my laser pointer. So, as I'm sure nobody will forget, yesterday the catering was up here in conference room 245. It is now all in this room here. So right next door, breakfast obviously was there. The food during the breaks will be there, as will lunch. I think some of you have raised this. I unintentionally lied yesterday when I said there was hot breakfast every day. There's hot breakfast every other day. So tomorrow there's hot breakfast, I promise. So also next door in the room are several tables and the poster session. Once Bastille launches their hacking challenges, which Ballant will be introducing later today, there will be stuff going on in there for that as well, including a scoreboard and a few other items. This is obviously the main track ballroom. This is where everything else is going to happen. This is not a multiple track conference. This is one track. Everything happens here. And lastly, our booth room, vendor room, sponsor room is all here. There are more tables in there now than there were yesterday, so during the breaks, there's definitely not enough room for everybody in there. Head into the sponsor room, and there are tables there. Okay, presentations. We now have a page online where we are posting presentations. You can find it by hovering over the schedule tab and going to talks. I was just informed by Dr. McGuire at VT that this hovering thing doesn't actually work on mobile. I apologize. If you want to go to it, it's just theguniradio.org/grcon2016/talks. And as long as we have the slides from the presenters, and for the most part everyone has done that, as soon as a presenter starts speaking, we will post the slides online, as long as all of the at least one organizer is able to do that. Okay, parking. So hopefully parking was much smoother for everyone today. Quick show, did anyone purchase a parking ticket and not receive an email from the organizers? No, awesome, all right. So for everyone new here, this is your first day here, there are 2 lots that are easily available. The first one is here. This is a Euclid lot. It's right across the street. So as you turn into UMC, we're on the left. If you just keep going a little bit, it actually looks like a giant construction center, which it mostly is at this point. But there's a multi-story garage that is parking. The other location is up actually near where the reception was last night. There's a parking garage there. And if you would like to park in these 2 places, if you do it on your own, it's like $36 a day. We have now tickets on Eventbrite, where if you buy the ticket, we'll email you a code, and it's $12 per day. Then you can buy it for basically the duration of the technical conference or the duration of the week. The other options are directly across the street. There's a commercial parking lot, University Hill Parking. That's right across Broadway. You also have a number of options downtown. If you want to park up there and walk, it's about a mile or a mile and a half. Other modes, people have been Ubering and Lyfting, and these seem to be working pretty well. At least one person is using the bicycle share, which is $8 a day, and then obviously walk. So organizers, this is the organizer list. We have a pretty good crew from both the GNU Radio Foundation as well as the University of Colorado Boulder. If you have any questions or need anything, feel free to find us. It says organizer on our badges. So with that, I'm going to introduce our keynote speaker, and if you want to come get hooked up here. Oh, and actually I forgot one last thing. So at the CU Boulder booth, they're running a raffle every day. If you drop your business card in, you can win some CU swag. So the winner from yesterday, and I'm horribly sorry to whoever this is, I'm going to butcher your name. I think it's Dr. Vesa Vaskalainen? Is anybody? Yes, you won. All right. Okay, well, I am very pleased to introduce our keynote speaker, Dr. Charles Clancy. Dr. Clancy is an associate professor of electrical and computer engineering at Virginia Tech. He directs the Hume Center for National Security and Technology. Prior to joining VT in 2010, he served as a senior researcher at the Laboratory for Telecommunication Sciences, a defense research lab co-located with the University of Maryland, where he led research programs in software-defined and cognitive radio. Dr. Clancy received his BS in computer engineering from the Rose-Hulman Institute of Technology, MS in electrical engineering from the University of Illinois, and his PhD in computer science from UMD. He's a senior member of IEEE, has over 150 peer-reviewed technical publications. His current research interests include cognitive communications and spectrum security. So please welcome our keynote speaker, Dr. Clancy.
All right, good morning. Let's move that down. And thank you. This morning I am going to be talking about some really interesting work that we're doing at Virginia Tech in the area of deep learning as applied to digital signal processing. A lot of this work is work that Tim O'Shea has been leading as part of his research at Virginia Tech, and so as a good PhD advisor, I just steal all of his results and claim credit for them. If you want to, I'm going to cover kind of the high-level overview and motivation. For a lot of the gory details and some of the current results, check out his talk on Thursday, which will go into a bit more detail. So, I am from the Hume Center for National Security and Technology. We do lots of interesting work. We've been working in the area of software-defined and cognitive radio for the last, ever since we were established 6 years ago. And lots of different applications of that, principally in the defense arena, but also a variety of commercial applications as well. We also have a large graduate student population, and some of you companies here already are working with us as part of trying to recruit some of our students, but we do have a lot of students who've been doing a lot of interesting research in this area. So if you're interested in that, please feel free to reach out. And as I mentioned, we also do lots of interesting research as well. So, getting to the topic though. So my talk is kind of broken into two segments. The first segment is kind of sort of doom and gloom as far as the future of software-defined radio. And then the second is sort of what we view as kind of the opportunity for growth. So, if you think about the trajectory of radio, this is what radios used to look like. Maybe, 50 years ago? You've got inductors and transistors and capacitors and resistors and op amps and all sorts of things, sort of traditional hardware radio. When software-defined radio came along, the idea is, well, we don't need this anymore, right? We can replace all of this with digital signal processing. And the process that people went through was very informed by the sort of building blocks that we started with in the world of hardware radio. So if you kind of want to know what all these individual circuits are, well, you've got some sort of antenna, there's a filter, there's a mixer. That mixer is mixing some oscillator that's doing the tuning. There's some sort of amplifier, some sort of low-pass filter. In this scenario, we're doing envelope detection and filtering that and putting it through an amplifier and playing it out of speaker. So even in the world of hardware radio, radio engineers are kind of building their hardware radio from sort of radio primitives, much like you find in the world of digital signal processing. So again, you're kind of gluing together pieces that are ingredients in a larger recipe for the radio that you seek to design. So I would contend that as we moved from hardware radio to software radio, we weren't particularly innovative in how we did that. It was a fairly one-to-one replacement where we took something that was a collection of inductors and capacitors and resistors, and we replaced it with an algorithm that did precisely the same thing as the original component. So if you look at this, what starts to kind of look like a flow graph in the world of hardware radio, you'll find that it looks a lot like a GNU radio flow graph. Very similar components. Obviously, the labeling's a little bit different. You have to deal with kind of the whole world of digital and the impacts that has. But again, it's a kind of one-to-one relationship to the underlying components of hardware radio. It's also based on a century of expert knowledge in how we do radio engineering. It goes all the way back to the turn of the century. So again, we're basing this on a progression of best practices in radio engineering that kind of evolved from the turn of the century up through the 1950s. We're taking that and doing this sort of one-to-one replacement with algorithms that do each of these components instead. So I would contend that that is sort of an incremental evolution that we've seen over the last 20 years, and it's been pretty transformative in the places that it's been applied, but I also contend that it is sort of a limiting view of how we could potentially do digital signal processing in the future. Now, alongside software-defined radio, we have the world of cognitive radio. The flexibility of software opened up the ability to do dynamic waveforms, reconfiguration. This then was, the search space was kind of too large to sort of manually manage. So the notion of cognitive radio was, let's put some sort of machine intelligence in charge of the configuration of our radio, and that will significantly improve performance. So over the last maybe 10 or 15 years, we've seen a lot of interesting research in cognitive radio. And I would generally break them down into 3 basic buckets. So if this is our sort of nominal radio design, obviously there's lots of different flow graphs and radios out there. So this is sort of a nominal design of different components. The first thing we did was we had to instrument it. We had to parameterize each of these components so that we could make changes to them. So the first thing I'll do is add sort of ports to each of these that expose a set of configurable parameters that, in theory, some sort of third-party agent could configure. Now, in a more traditional radio system, it's going to be some sort of user interface where the user is configuring these radio primitives. But in the world of cognitive radio, the idea is we've got machine intelligence that's doing that. So probably the first application that really took hold was that of dynamic spectrum access. So we began sensing the spectrum. We then used that information to essentially determine the center frequency that our radio system should use. So if you look at sort of the history of cognitive radio, probably 2004 to maybe, well, actually it's through today now. I mean, the applications have changed a bit. But that's been one of the key driving applications of cognitive radio is dynamic spectrum access. What we see right now, particularly, for example, in the 3.5 gigahertz band here in the United States, is the deployment of spectrum sharing systems. Again, it's based on some of these basic principles of being able to dynamically change the center frequency of your radio system. So application number 1, I'll contend that is been, again, fairly transformative in how we manage spectrum, but it's not really that cognitive in my opinion. Application number 2 is really more waveform adaptation. We have a waveform, we've got lots of ability to change the configuration of different components, and we're pulling metrics, performance metrics out of the radio, things like signal-to-noise ratio and bit error rate, and we're using that to reconfigure the radio in some way. So here we might be changing the modulation, constellation that's being used, we might be changing the rate of the code. Again, these are fairly straightforward technologies. Wi-Fi, for example, right, has rate adaptation based on channel quality. The SATCOM community has used it with adaptive coding and modulation in DVB-S2, for example. So again, it's sort of cognitive principles. You've got some sort of algorithm that's trying to decide how to configure your radio in order for it to perform the best in a particular scenario. But again, the search space is small, right? If I've got 5 different modulations to pick from and 6 different coding rates, I have a search space of 30 different possible configurations. So it's fairly easy for an algorithm to pick among 30 options based on some fairly straightforward inputs that it would use to make that decision. I think where cognitive radio has not really made as much progress as many people thought it would when it was first introduced about 15 years ago was in the notion of these truly dynamic waveforms. So certainly GNU Radio, for example, has the ability to rewire your flow graph on the fly. There's some sort of gymnastics you have to go through with the scheduler to keep it from crashing, but it's possible to sort of rewire your waveform, swap in and out components for a running flow graph. And so this is kind of the sort of future state of cognition that many people thought would be the norm, where we would be able to custom design a waveform that was most suitable for a current channel condition, a current set of circumstances, a current set of users and their applications. And we haven't really seen that, really, in terms of any sort of commercial adoptions, certainly. There have been, obviously, some research examples of being able to do this. So, and I would also contend that this has eluded us principally because the search space is entirely too large. Now I'm looking at GNU Radio as a bag of blocks, and I need to pick some permutation of those with some input parameters that then would create a waveform that is optimal under some sort of optimality criterion. And again, that permutation is very large, and searching through it is difficult. So this, I think, has sort of eluded us with the exception of a handful of very specific applications where you can significantly constrain that search space. For example, maybe you're able to swap the order of the scrambler and interleaver or something. Some fairly straightforward things like that I think are feasible, but sort of building complex waveforms cognitively hasn't really happened. Again, it's a computational complexity problem in my opinion. The search space is too large. Another thing I think that's important when we talk about cognitive radio and software radio and where things are headed is Moore's law. So here's Moore's law, starting all the way back in 1970 up through last year. We've got all of the Intel product lines, dots in blue. We've got all the PowerPC blocks here in red. And if you look at the evolution of Moore's law over the last, well, since forever, up until about 2005, 2006, 2007 timeframe, it was all about clock speed increases. These were all single core processors, and we were shrinking the fabrication process technology, which allowed us to use higher clock rates. So we're getting up here through, let's say, Pentium 3, Pentium 4. In these scenarios, these are still sort of single core processors. It wasn't until we kind of maxed out at roughly 3 gigahertz in clock speed that Moore's law took on a fundamentally different shape. Since we maxed out at around 3 gigahertz in clock speed for silicon, Moore's law moved into parallelism. So we started adding cores. So we went from single core machines to dual core machines with hyperthreading, quad core machines. Once we kind of maxed out that area, we saw the rise of GPUs with significant density of multi-core computing. So we're continuing to increase the theoretical flops in a processor, but we're doing so in such a way that requires parallelization in your code in order to actually be able to effectively execute. So I'd say that this is also a challenge for the software radio community. There's been lots of research ongoing. I'll talk about a couple things here to try and harness that, but again, it's challenging. So how are we doing in the world of software radio? So I've added to the right hand of this plot sort of instantaneous bandwidth that we could effectively process in real time. And if we put kind of advances in USRPs and GNU radio running on a typical commodity desktop computer, we basically see sort of this trajectory. Back right when GNU radio was first released in the early 2000s, here we've got, say, a Pentium 2 with a single core hooked up to a sound card, and we're processing maybe 50 kilohertz of signal bandwidth in real time with that system. As you continue to move up, we have the USRP 1 hooked up to a Pentium 4. I mean, in theory, you can pull 6 megahertz of bandwidth across the USB interface, but in reality, the computers of the time had difficulty processing any sort of sophisticated waveform with more than, say, 500 kilohertz of bandwidth. As we continue to move forward, we've got, say, the N210 with a Core 2 Duo. We're now being able to process upwards of 5 megahertz of bandwidth. People are doing DTV-type signals in real time at that stage. So again, we're kind of continuing to track forward. And then now, I guess you could kind of argue what the cocktail of choice is, but let's say you've got an X310 running RF NOC and it's hooked up to some multi-core i7, right? So we're now in the regime of tens of megahertz of instantaneous bandwidth that we can process in real time on these platforms. So it's very interesting growth. We are sort of literally tracking Moore's law here because, again, we're basing this on some commodity desktop computer that this is being hooked up to. And so you can kind of track the processing bandwidth. Now, a challenge that the software radio community has had is that commercial wireless is not in that same plane, right? Commercial wireless is up here. So if you look at GSM coming out in 1995, that's got a 200 kilohertz transponder. GSM base station is obviously running multiple transponders. You may have 7 or 8 transponders on a single tower. So you've got a pretty significant processing gap between what's possible and what's required to do the sort of waveform of the day in software. And some might contend that this gap is, for example, some of the challenges that Venu had with his spin-off of GNU Radio back in the late 1990s. Again, UMTS, LTE, 802.11n. 802.11ac, we're talking 160 megahertz of bandwidth. I mean, that's a big number. That's a big number to do in software. Trying to do 4 channels, 160 megahertz, MIMO on Edis hardware with commodity desktop computer. Again, that's something that'll be possible in presumably a few years if we can continue to track Moore's law, but it's not possible today. So this gap has I think, many people has helped. It's hampered the ability for software radio to be wholesale adopted into the commercial wireless ecosystem. Obviously, there are certain applications where it's becoming successful. There are components and philosophies of software radio that are showing up in RF baseband, ASIC design. But again, we're not running GNU Radio on our phone. The Qualcomm processor in our phone is not running GNU Radio. So how do we get there? And how do we keep, even if we don't sort of have a leap up so that we can catch up with the commercial standards, how do we maintain this track when this is becoming increasingly parallel in nature? And I think that's what I just said. So let's go back and look at the fundamental signal processing challenges that we have. So let me go back to my, my nominal radio flow graph, where you're doing some sort of tuner, an analog to digital converter. You've got a modem. You're doing some sort of interleaving and scrambling. You've got a coder and some sort of framer at the end. Again, sort of my nominal SDR flow graph. This is an inherently serial process, right? I can't run all of these in parallel because I need the output of step n to become the input of step n plus 1. So we have some fundamental challenges right off the bat with parallelism in a feed-forward sort of serial flow graph mentality, which is really how software-defined radio has defined itself over the last decade or two. So how do we get parallelism out of this? Well, first thing we do is, what it was, 2006-ish, GNU Radio introduced the thread per block scheduler, which was timely. Up until that point, most desktop computers were sort of one core and a single-threaded scheduler. The original GNU Radio scheduler worked well. You only had one core. Why do I need parallelism in threads? Well, mid-2000s, we're now seeing multi-core, hyper-threading, all of these new capabilities coming along in the processor technology. At that point, we needed the thread per block scheduler on GNU Radio, which allowed each of our blocks in our flow graph to run in their own thread, and they had circular buffers between them that they used to feed information from one to the next. So this was good. It allowed us to now take advantage of multi-core. We were able to increase the total processing done on a sort of computer of the day using this threading, because we're now creating this pipeline of data that is flowing through. The second major advance that we saw that was morely kind of in that same era but I guess the next couple years after the thread per block scheduler, were other forms of parallelism. The first is single instruction multi-data, or SIMD. These are the SSE extensions that you'll find in modern Pentium processors. This had a pretty significant impact on the performance of many GNU Radio blocks by being able to do vector math, and things like convolutions could now be done 4 times faster than they could before by taking advantage of the vector processing capabilities that you have in your standard processors. The other advancement that we began to see is the world of instruction level parallelism, where you have multi-issue pipelines and you're able to issue multiple commands simultaneously. Those of you who do a lot of sort of TI C6000 DSP programming are kind of familiar with this notion of instruction level parallelism. But it hasn't really shown up in the world of commodity processors in the same way. There have been a few boutique processors along the way, such as the IBM Cell Broadband Engine, that had processing elements that had inherent instruction level parallelism. But where we will find ILP now is really in GPUs. GPUs are the ILP engine of now. So the question is really, how do we take advantage of the ability to do instruction level parallelism? And if you think about how you graft GPUs into this serial feed-forward flow graph, the approaches that people are typically using have consisted of essentially a block of code. Now, an interleaver is maybe not the best example. Maybe a coder is a better example for GPU offloading. But you've got your block that's doing your decoding. It creates a kernel of work. Maybe it's using CUDA. It issues a call off to an NVIDIA GPU that's going to then process that. It's going to block, waiting for the return of that data to come back, and then that data is going to continue forward in the flow graph. So essentially, this thread is blocking, waiting for the ILP to happen on the GPU. And these three things have allowed GNU Radio to take advantage, to a certain extent, the available parallelism that we have in modern processors. However, I contend that there's problems. First, when you introduce a threaded pipeline, you inherently introduce latency. My clock is still running at 2 to 3 gigahertz. So if you think about the amount of work that needs to happen to go from raw IQ data to processed packets out the other side, or vice versa on transmit, it's the same total number of clock cycles that was required. So even though I'm breaking it up and running it in multiple threads in order to increase the amount that I can do in aggregate, I still have the same latency. So the clock speeds are not increasing, which means as we go from processing 1 megahertz signals to 10 megahertz signals, since our clock rates aren't increasing, we're seeing a 10x increase in latency through the system. So at some point, latency is going to kind of kill us to the point where we're not able to effectively take advantage of software radio. Sort of one anecdote from several years ago when we were working on a project for a fairly complex commercial wireless waveform. We had, I think it was like a 64-core server. We managed to get this 20 megahertz waveform up and running in real time, no samples being dropped, process going all the way through on a heavily loaded signal. But we saw 8 to 10 seconds in latency going through that pipeline because there were so many pipeline stages required. So again, if you have 8 to 10 seconds of processing latency, you're not going to be relevant for any sort of commercial applications where you need to be interactive and send acknowledgments to packets, right? So again, latency is a key challenge as we cope with trying to get parallelism out of an inherently serial process. The second is that, particularly for the world of ILP, we have this coprocessor transactional latency. So every time I issue a kernel of work to a GPU, that doesn't happen for free. I have to wait for that code and that data to be sent over some sort of bus, be DMA'd into the memory of the GPU, and then the code be executed there, and then I have to wait for the results to come back. And so while the actual execution of the code is perhaps faster, there's the transactional latency of sending the data there and waiting for the data to come back, which is another key challenge that we have with leveraging things like GPUs. SIMD, on the other hand, is basically free extra processing. There's no kind of downside to that, so hooray libvolk, I guess. So as we look at the challenges, I think this is just fundamental math. You can't really get away from the latency challenge. That's why I would characterize much of the core research in the world of software radio over the last couple years, and in fact, the topic of one of my PhD students' dissertations is figuring out how to mitigate this coprocessor transactional latency. And I know probably many people in the room at some point have looked into this and tried to figure out how we can better take advantage of GPUs for signal processing. So I guess the message I want to paint is that we are getting close to being able to eke out all of the remaining parallelism that's possible in some of these flow graphs. Signal processing is inherently serial, and we can continue to dice the pipeline into smaller and smaller steps in order to get parallelism sort of horizontally, but that's going to continue to increase latency, and there's very few opportunities to increase parallelism vertically in some of these environments. So again, GPUs, I don't think we're going to be able to fully harness GPUs to the full extent. There are obviously other efforts going on, things like RF-NOC, where we're trying to take advantage of non-von Neumann processing architectures and take advantage of FPGA fabrics, for example. I think those, again, are going to be able to take advantage of the increased transistor count that are on these processors. But I sense that we're going to hit a scaling limit in terms of the ability to catch up to the commercial standards, certainly. And I would wager that it might be difficult to even continue to keep on sort of the track of Moore's Law. So that's my doom and gloom half of the talk. Any questions before I jump into the next part? Bob.
In 1988, Motorola, with their DSP 56000 family, was doing ILP.
Sure. Yeah, I mean, certainly ILP has been in DSP blocks for TI, for example, TI and Motorola and others have been using it. It's kind of interesting. The software radio has kind of not taken advantage of the embedded DSP environment in the same way that it has FPGAs and GPPs, which I think is kind of interesting. I don't know, maybe there's a role for embedded DSPs. Bob says no. Any other questions? Dan.
You talked about GPUs and their limitations. Do you see FPGAs? You talked about FPGAs, or I'm sorry, GPUs as having limitations. Do you see FPGAs as being the saving grace here?
I think FPGAs don't have the same scaling limitations that we'll find with GPUs. I think the challenges with FPGAs are different. I think it's the software development time and the reconfigurability and the sort of speed of development is a key challenge. And again, I think RF knock is doing a great job at beginning to shift that into making them more usable. So again, I think that's a really important thread of research that is a key to maintaining our track of Moore's Law. Bob again?
Yeah. So you use Moore's Law, Kootenai's Law, K-O-O-M-E-Y, is a better law, and shows that we have a further ways to go, going up the joules per calculation curve, and there's where you really begin to see FPGAs take off. If we can solve the programming, use of, reconfigurability of issues with FPGAs. Kootenai's Law should replace Moore's Law in all of our thinking. It's been accurate since 1957 and continues to be accurate.
Okay. All right, well, let me jump into Act 2, the hammer we are developing at Virginia Tech that is useful for all nails. So, well, how can we design a radio that has inherent parallelism? I contend that because we started off with these hardware radios, that we then incrementally moved into, we took the same RF engineering design that we used in hardware radio. We did a one-for-one replacement with DSP algorithms, and that produced what was inherently a serial process. But what if we re-envisioned how we should fundamentally do digital signal processing? Think about the human brain, for example, right? We are able to take in sensory information, both visual and audio, and in very low latency be able to process it and do feature recognition, demodulation, and processing. And we don't have these challenges of having to necessarily wait for our brain to finish processing the visual image in front of us or the audio that we're hearing. So what is there about that kind of signal processing that we might be able to leverage in the world of digital signal processing? So, for example, can we somehow leverage the world of artificial neural networks to solve this problem and do digital signal processing in a very low latency manner? And we have kind of an enabling opportunity here. We have this buzzword called deep learning that has gotten a lot of people excited over the last 3 or 4 years, particularly in the world of video image processing. And they have had some significant results that show that it is able to do a lot better than some of the classical neural network algorithms. And so the question is, can we apply the advances that we've seen in other fields in using deep learning to the challenges of digital signal processing to overcome these scaling issues that are going to otherwise prevent the continued growth of digital signal processing. So one might contend, haven't we been applying neural networks to software radio for the last 10 years? I mean, I know I've been publishing papers on some cognitive radio thing that uses a neural network, right? What's new, right? So what has fundamentally changed, and what am I talking about that's any different than all the neural networks that people have been using in the world of cognitive radio for the last 10 plus years? Well, this is kind of your grandmother's neural network. You have an input layer, you have maybe a couple hidden layers, and then you have an output layer. And you train this thing by feeding it input on one side, and you feed it trained output labels on the other, and then the weights associated with all of these interconnects begin to converge, and it basically creates a network where you give it an input, and then it gives you that trained output. So it is essentially trying to solve a dimensionality reduction problem, where I feed in some typically higher dimensional input, and it needs to give me a lower dimensional output, and it's trying to converge upon some sort of optimal dimensionality reduction transform. Well, what we've been doing, in our research over the last 15 years, essentially we've been taking, I don't know, modulation recognition is a common example. You'll take some input RF signal, you'll compute expert features from it. And I can't tell you the number of papers I've read on cyclic cumulants or cyclostationary features or high order moments. There's all these different expert features that people will extract from some sort of RF signal. They will take those expert features and they will plug them in as the values in this input layer. And they'll train this network and then be able to do the same modulation recognition as the underlying objective. So again, you're solving what is, you're doing a lot of the work ahead of time by picking these expert features. And you're also presuming that it's not going to take very many steps to get from those expert features to the answer. If you think about this, this is sort of a, I mean, with this number of layers, you've got basically a quadratic relationship that you're forming between the inputs and outputs. And not every relationship in the world is interpolation of some sort of quadratic relationship, right? Many relationships, such as the RF energy coming in my cell phone and the SMS that then appears on my screen, that is much more complex than just a quadratic relationship between input and output. And so what the world of deep learning has essentially done is say, we can't get away with just two hidden layers. We need much more complexity in our neural networks. So this is a diagram from one of Tim's recent papers where he's showing lots and lots of different layers, and these layers all have different structures to them. So you've got convolutional layers, you've got fully connected layers, you've got dropout layers, you've got softmax layers, you've got all these different layers that are all interconnected in what looks a lot like some sort of data processing pipeline, if you will. So again, you're able to form a much higher order relationship between input and output than you can with a simple sort of 2 or 3 stage neural network of yesteryear. And so this is the fundamental premise behind deep neural networks, is this notion that they are deep, right? You've got lots of stages of processing along the way. So if we form networks like this, can we actually do signal processing with them is the question. And the answer turns out to be yes. The other interesting thing that I think is really kind of exciting about this is if I look at building a network such as this, it's gluing together existing sort of primitives to take input data and produce output data, which sounds a lot like a GNU radio flow graph. But again, this is a fundamentally different structure. This isn't specific signal processing blocks that I'm composing in some sort of expertly chosen order. This is a bunch of neural network components that I am somewhat heuristically gluing together and tweaking to hope to improve my bit error rate on the other side. Which is, again, kind of a critique of the whole world of neural networks is there may be multiple network structures that give you good performance and some very similar network structures that give you bad performance. and we really don't know why one works and why one doesn't work, which is sort of still a challenge with kind of understanding the theoretical properties that underpin this whole world of deep learning and deep neural networks. So right now it's kind of sort of you still have an expert component, but now it's not an expert in radio engineering who's deciding I need a convolution at this point. It's more an expert in machine learning who's deciding, oh, well, intuitively, we need a dropout layer here. So that's kind of where the trade-off is, I guess. So this network here actually is from one of Tim's papers, and this is actually doing demodulation to a certain extent. It's producing sort of soft symbol outputs. You've got raw RF data coming in one side. This is doing equalization to the channel. Then you're over here essentially doing synchronization, and sort of the output of this is a sort of a constellation. And some of the initial results, and I've got a couple graphs later on, show that, yeah, I mean, this is possible. You're able to build something that can do demodulation of narrowband modulated signals using something that is purely a neural network. So why is this exciting? Why do we care about this rather than just doing what we've always been doing, right? So if I'm able to get something that is almost as good as the expert radio engineer designed signal processing performance, why would I want to adopt this whole new crazy environment rather than just continue to do what I'm doing? And the answer really is that of parallelism. So this is extremely parallel, right? You still have a serial component to it, but each one of these blocks is extremely parallelized. Training these networks and executing these networks can be done with, again, extreme parallelism. So it allows us to fundamentally get past this heavy serial component that we have in traditional signal processing and replace it with something that is inherently parallel. We have all kinds of cool tools that are showing up in the open source world. TensorFlow is just one of many examples of basically neural network algorithm toolboxes that are specifically designed to run blazingly fast on GPUs. So again, each one of these now becomes sort of a TensorFlow block, and you use these new design tools to create GPU workloads. And guess what? These GPU workloads can just all live on the GPU. You're not constantly dispatching small kernels of work to the GPU, blocking on a result and waiting for it to come back. So you get over some of these fundamental things that introduce latency into the traditional signal processing environment. So that is why we want to do this. Well, it's one of the main reasons why we want to do this, is so that we can actually exploit these highly parallel environments rather than continuing to be stuck with the sort of GPP environments that we've been using so far and the challenges of trying to use GPU environments. So then that question is, do we end up with a scenario such as this, where we essentially have raw RF going into a big neural network and out comes data, right? That's sort of the asymptotic version of where this research could eventually lead. And obviously, we're not even remotely there yet. There's probably another 5+ years of research that needs to happen before we are kind of able to do something like that. But it's a really exciting opportunity. And then previously I talked a bit about cognitive radio and the challenges we have with cognitive radio and scaling of cognitive radio. Again, it was a computational complexity challenge, right? Being able to figure out which of these flow graphs is optimal for a particular scenario, the time it would take to solve that optimization problem was too great. So this was infeasible. But I would contend that, again, we were constraining our solution, right? We were presuming that the solution had to be a set of GNU radio blocks composed in a particular order in order to be the solution. And I would say that if you ignore the underlying need for a GNU radio block and the need to compose them in a particular order, you then can essentially learn entirely new waveforms, and you don't have to worry about rewiring a particular flow graph. Now you're just retraining weights in a neural network, and it's fundamentally changing the underlying properties of your waveform. So I believe that while we haven't really even begun to explore all the possibilities for fully cognitive waveforms with this, I believe there's a whole bunch of opportunity there as well. So in an effort to steal some of Tim's thunder, here's a couple of results, so it's not too hand-wavy of a presentation. So this is a paper that Tim published recently that's looking at signal classification performance. And these are some older results. He's got some newer results that are even better, but these are the ones that were published online, so I stole these. Interesting results here. You've got kind of classical approaches to signal classification, which are all these dashed lines, and then you've got the approaches that are based on these deep neural networks and convolutional neural networks, and they are all the solid lines. And of course, you see the solid lines are higher than the dashed lines. So we are meeting or exceeding the performance of traditional signal processing algorithms. In some of his newer results, he's even a few dB better than the traditional sort of expert features plugged into a support vector machine, for example. So, okay, we're able to meet or exceed performance. Exceeding performance is great, but we're only exceeding performance by maybe a couple dB, so maybe that's not earth-shattering. What's really, I think, particularly interesting, though, is this number right here. This is the time it takes to do that classification. We're able to do a signal classification 30 times faster using this network than if we were to do a traditional feature extraction, feed that into a support vector machine, and get an answer out. So this is the opportunity for orders of magnitude swap improvement. And if we can get orders of magnitude swap improvement in our ability to do digital signal processing, we are able to close this gap right here, right? This gap is maybe a 10 to 20x gap in performance. And again, this is just one example of signal classification, but we are seeing 30x improvement with roughly the same performance in terms of, well, actually, so 30x improvement with a modest increase in overall performance of the signal classifier. Now, the trade-off you have is training, right? These neural networks aren't just going to run out of the box. You have to train them. So you need lots of training data, and you need lots of label training data. And training these networks is not cheap. It takes the computational time it takes to train these networks can be significant. However, we have this great thing called GNU Radio. And GNU Radio can produce an infinite amount of training data when designed with sort of expert knowledge of how to build a waveform and how to build a channel model. So if you're able to take GNU Radio and use it as an engine to train these neural networks, you're now able to see these 30x level improvements in your runtime performance by doing that training ahead of time. So I see that as the key advancement that we'll be able to see, or one of the key advancements that we'll see, particularly on the digital signal processing side of deep learning. So then you just need a big GPU machine that you can sit and run a bunch of data through. Tim will talk about his existing data sets that he's built that he's been using for training during his talk. These training sets are all available online for other people to start playing with. But yeah, you've got to train it. So you can almost think about it as you've got sort of a century of radio engineering knowledge that has been sort of dumped into GNU Radio in the form of waveforms and flow graphs and blocks. And if you can compose those, you can then do almost a knowledge transfer into these neural networks through the training process that then produces something that can run much faster and with much higher parallelism than you'd be able to use if you had a traditional processing flow graph. Some other recent results. This is learning to communicate. So this is getting more on the cognitive side. So before I was talking about cognitive radio has suffered some limitations because we can't, it's just not feasible to build a flow graph from scratch that's custom designed for a particular environment. In this environment, it actually could be. So this is, again, some results from a recent paper where we were training a neural network to design a waveform from scratch that would be ideal for minimizing bit error rate in a channel that it was presented with. So, I mean, who knows how it actually did the encoding, right? That's, again, part of the issue some people have with neural networks is how would something other than the matching network know how to demodulate this thing? But again, you can think of a dimensionality transform where you need to take bits of data, you need to transmit them through some channel, and that channel has some kind of nasty channel effects, and then you want to get those same bits out on the other side. And this is really just an an error correcting code process. You've got to add a bunch of redundancy, and then you've got to remove that redundancy on the receive side. So if you think about basically digital communications as adding redundancy and removing that redundancy, and you're not constrained by the typical composition of GNU radio blocks, there's a lot of interesting things that you can come up with. Maybe a Fourier basis makes sense. Maybe a Fourier basis doesn't make sense. It all depends on the delay spread of your channel and what your multipath characteristics look like. We might be able to it might come up with some crazy wavelet modulation. You don't, that's the point is, you don't even know. It's coming up with something that it is training and deeming to be optimal for that particular channel and specifically tuned for that particular channel. So again, here's just some examples of building something that's able to transmit data over an RF channel with lots of nasty channel effects. And here we see the two dashed lines are the theoretical capacity that we would see with QPSK and 16 QAM in terms of bit error rate as a function of EBNO. And then this is a variety of different things where we're able to kind of match theoretical we're actually able to exceed the theoretical performance of some of these sort of traditional digital modulations. Again, very interesting. A lot more research that needs to be done before we can figure out how to actually do something productive with all of this. And I think that's my last slide. I will essentially give forward pointers to Tim's talk on Thursday, and then Seth Heightfield's talk this afternoon. He's going to be talking about some of the GPU work that we've been doing. So, fun stuff. Oh, yeah, and there's, I think Virginia Tech has stolen half the agenda, so.
Yeah, so we do have time for questions. We have a lot. Okay, so Michael and Jose are in the audience. All right, so Michael and Jose, I think if you can come up front here for the second question. Go ahead, Raj.
It seems like a lot of the difference between those two curves, the commercial curve and the Moore's Law SDR curve, is accounted for by custom silicon. If I'm not mistaken, that's why GSM and UMTS and LTE can do what they do. So do you see any role for custom silicon on that other curve as a way to jump up?
Well, it's not software defined at that point. If you're constraining your solution space to software defined digital signal processing, then it obviously is sort of not in there. But you could imagine building custom ASICs that are just sort of a big grab bag of different underlying primitives that could then essentially be wired into your flow graph. I don't know if there's a business case to be made there, but that's certainly within the feasible solution space.
So you talked a lot about latency at the beginning. Did you have any latency numbers for the analysis you were showing there at the end of the deep neural network?
Yeah, I mean, the latency, it certainly didn't take longer. I don't have the numbers offhand, though. We were just looking at this is in seconds, so I guess that is inherently latency. Again, I don't have the underlying data of what platform was being used and whether it was a GPU or not. So this is sort of a round metric. But yeah, 30x faster or 30x less computational requirements for the same latency, I guess, is the sort of simple trade-off there.
Somebody can get to Bob.
Bob?
Go to the serial flow of neural network blocks. Okay, so yeah, you made exactly the right comment. In a brain, in the real brain, the way these neural networks are laid out is every one of those layers is connected to each other, and they have tons of feedback. All the feedback in our training of these serial neural networks is done by backprop, which is a poor substitute for direct feedback connections. So that's one thing. Thing one. And the need for us to be able to do that is captured in the example you had in mind of the complex commercial waveform where things were changed downstream and upstream they needed to be understood. Right. There's all, as Charles said, the race to get kind of all of this right is pretty amazing. This is amazing results, but you can kind of see from how the brain works and how we need the complex things to feedback, and the underlying theoretical stuff about why this works is the representation theorem, which says any function can be represented by these neural networks to within epsilon, where you pick epsilon. And then there's the generalization, which we do every single day. It's not possible for you to have seen everything, but once you come on a new scene, your brain says, this is something like this, therefore I'm going to proceed as if it were something like this while constantly getting feedback, so I retrain my brain. So the generalization is important. These are terms you can go find in any set of literature, but this right here is an amazing result, and I think we're going to see really huge impacts for the continuation. We need something in addition to a GPU so that we can capture all of that feedback we need to be actually like a brain.
Yeah, so things like memsistors, things like that, there's some fundamental new building blocks in silicon that would really help with further improving the performance of things like this.
So I'm going to jump in here and also make a statement, and I will try to finish up with an actual question. So back to your the slide again about that, the difference between software radio and hardware radio. You know, obviously we want to make everything bigger, faster, stronger, better than before. But one of the things that I caution in an open source world is to never try to chase the commercial product. Octave is never going to beat MATLAB. LibreOffice, as we've already seen yesterday in this conference, as you'll probably see later through this week, not going to compete with Microsoft Office. Great that they're there, but they're not competing. So I don't know if it's really the right thing to try to chase these commercial standards, because why not just buy the silicon that does that?
Sure. So I will, first I'll say that I don't see these neural networks replacing 3GPP anytime soon, right? There's just so much efficiency that you're going to continue to see out of these custom silicon designed for these specific waveforms that I don't see us overtaking that soon. So I completely agree that that shouldn't be an objective. I was just using it as one measure of sort of performance gap, I guess.
And I think that's good. So then the question really is, so you brought this up, what is the business case for the software radio trying to do something, maybe not compete there, but what's the business case for doing something else in the software radio space where we're trying to push for?
Right. So again, I don't see us replacing 3GPP in the next n years. I don't know what n is, but there could be n+1, again, depending on the value of n, where maybe it would be feasible to replace some of these very complex standards. I don't know.
No, sorry. The question really is so the whole idea of software radio is in its flexibility.
Right.
What's the other use case of that flexibility as opposed to a single purpose thing we could do in silicon? We know how to do that really well. Great. Let them have that. Sure. What are we doing? Where's the other business case? Where's the other use case for the flexibility and the power in that sphere? That's just, so let's get rid of that slide so we don't think about that. What's the case of where software radio becomes really cool and really important?
Well, I think software radio is already very important in terms of waveform prototyping and research and development. I think that there are lots of defense applications as well that are relevant. I don't think that, so I could imagine scenarios where defense applications of this would help sort of boost some of the DoD waveforms closer, perhaps, to some of the commercial waveforms, given that they are heavily software-defined, thanks to sort of the legacy of JTRS. So, like I said, I think some of the applications that make people money are going to be in the defense area in the next, say, 5 or so years. As far as applications out past that, it's hard to tell. I was meeting with a VC recently, and we had TensorFlow's logo on our slide deck, and they just got super excited because of the logo, right? So, Matt?
So you said one thing that you have to use, you can use GNU Radio as a tool to generate kind of, training sets. But you mentioned that you had to use label training data. So I've been out of the VT game for a little while. Are you guys looking at unsupervised networks, supervised networks? Does this kind of apply to both?
Depends on the application. So the sort of signal processing, sort of demodulation topic, or the feature, the waveform recognition, signal classification, that all requires labeled training data. However, this last one here, the learning to communicate, this is all unsupervised, where you're taking your input bits and then you need your output bits to match your input bits. So and it's doing all of the inside training in an unsupervised way.
Yeah, and I guess my question kind of comes from, I can see a world where maybe you want to classify 6 different modulations, and so you use training data or whatever. That's supervised as labeled. Mm-hmm. But in you saying that the theory for why this all works or how it works is kind of far from where it needs to be, I can see, like, even further on down the line, we need to optimally transmit these bits in some way given these circumstances, and that could be completely unsupervised. And that's even scarier theoretically, because it's like, we really don't know what's going on. Like, it might not line up with 16 QAM or whatever.
So these results right here are the first sort of proof point that you can do that.
You have his
Cool.
autoencoder slide? Tim's autoencoder slide?
I don't know, these are the...
Yeah, the autoencoder does like the minimum description link down the middle, and those handful of things that are in the center of the kind of autoencoder thing would do that.
Okay.
All right, so I think we have one in the back here.
Last question.
And Jose, could you get one?
Well, I think I'm
We have some more time.
Oh, we have more time.
Yeah, so Jose, if you could get Dan a mic or next, in the back.
So my question was, how much of this is open and out there so other people can try to reproduce your results?
So everything I've shown here, the papers are all either published in academic conferences or posted on archive. And like I said, Tim's talk on Thursday, he'll go through all of the data sets that are posted online already that he's been using,
All right,
among
thanks.
other things. Yeah.
All right, my question's in regard to creating data. So for like a fully functional cognitive radio, or at least approaching it, how are you going about creating the training data aside from like just making random noise? And like, are you using existing blocks in GNU Radio? Are you programming your own? Or are you just starting out with noise now? Like, how would you, for example, like interference or multipath?
So for training, if we want to build something that can process, let's say we want to build a neural network that can demodulate QPSK through a wide range of fading conditions. What we would do is, in GNU Radio, build a QPSK transmitter and then build lots and lots of different sort of channels that would go through. And we know the data that's being modulated by the QPSK, so that's the labeled output, essentially. So you have the modulated, you've got the data that you define. It goes into the QPSK sort of flow graph and generates the baseband IQ. You then apply a whole bunch of different channel effects to it. You then have the sort of normalized IQ output. That becomes the input to your neural network, and then the original data that you fed into your flow graph becomes the labeled output that you use to train. And so using that approach, you can have lots of different data. You can have an arbitrary sort of waveform structure that you want to learn, and you can have arbitrary channel effects that you want to be invariant to.
And are those channel effects, are those already in GNU Radio?
Mm-hmm. Yeah.
Oh, okay.
So these are things like clock drift and different multipath channel effects and all those sorts of things.
Dan?
I mean, you can do that with basically a FIR filter and a resampler.
You talked about how deep learning can be the method that we use to close the gap between software-defined radio implementations and the hardware. Mm-hmm. Once we do that, what's to prevent the hardware from starting to use those same techniques? Or does that necessarily just mean we won and they're software-defined too?
Well, I think what I would imagine that state to look like would be we would have hardware that specifically does deep learning. So I'd imagine you'd have the deep learning chip at that point. So that's my sort of futuristic speculation.
So, sorry, one more question.
We got some questions over here too, so not to tell Matt he can't ask a question, but.
All right, I'm gonna go. So, kind of the going back to your slide about kind of the old way that neural networks were done, and back. Yeah, so the part I think that you hit on that really sucked about this was that there was feature extraction usually being done fed into the input layers. So what it looks like to me is that now that feature extraction is almost getting moved into how you're structuring these deep neural networks. So is that, I mean, how are you guys like approaching that right now? Is it kind of arbitrarily like, it seems like that's where a lot of the theory needs to be ironed out.
Feature extraction has been abstracted into the neural network. So you've got raw IQ data coming into your input layer, not sort of expertly curated features being fed in. So that's all happening in the structure of the network itself. So we're kind of collapsing all that together into a single, again, and that's for a signal classification application. But yeah, that's signal processing too. Why not just learn the ideal features along? I mean, or maybe, right? So my presumption is that these networks are learning some ideal features, but it's kind of hard to know what they're doing.
Okay, we have time for just 2 more. So Stu?
So could you pop back over to the slide that said learning to communicate as a slide title? Right there. So the 1, 2, 3, the 4th layer isn't always the 4th layer. Sometimes we also go straight to the 5th layer. And that kind of alludes to a more general point that this doesn't really have to be a strictly feed-forward layered kind of a thing. But we now need some means of coming up with architectures for our networks. Exactly. So I wondered if you could address things like genetic programming and other perhaps forms of nature-inspired computation that might take into account that it's not just the tyranny of the weights, but also things like synaptogenesis and neurogenesis.
Exactly. So as I mentioned, there isn't a completely well-defined science to how you design these networks. There's people who, through experience, have sort of intuition behind what sorts of layers need to go where in order to do a particular sort of processing. And indeed, there are interesting research activities underway in other disciplines where they're looking at using things like genetic programming to determine the meta-parameter space of the network structure itself. It's akin to learning the flow graph of a GNU radio flow graph to a certain extent, right? We tried to apply genetic programming to that problem in 2008 and failed because the search space was way too big. But I think we can effectively apply it to this space because you don't have to be exact. There's a lot more room for error, I guess. You still get pretty good performance even if you don't have precisely the ideal network topology. So it'll be a more forgiving optimization problem, I predict.
All right, one more question. Nope, are we done? Oh, we have one, Jose.
I guess more of a comment. A number of times you use the word optimal, and I would caution against that. Neural networks are not optimal. Like they're not provably optimal. They're essentially a random search, and so a directed random search, and so you may be at a local minimum. So you can't really use the word optimal to describe these.
I completely agree. And that's one of the key criticisms of neural networks is you really don't know what's happening under the hood. And in many cases, you can sort of prove, based on knowledge of what optimal is, that you are approaching that in your network performance. But in scenarios where you don't know what optimal is, you don't know how good you are. So, all right, well, thank you.
All right, let's thank Dr. Clancy.